Imagine you are a detective. The crime scene is the entire solar system. And the clue is this: a planet. A planet we already know about is moving wrong. Not wildly wrong, not flying off into space, just subtly, persistently, stubbornly wrong. Moving a tiny fraction ahead of where it should be, then falling a fraction behind. Something unseen is tugging on it. The planet is Uranus. The year is the 1840s. And astronomers have been watching this quiet misbehavior accumulate, observation by careful observation, for 60 years. They've checked the data. They've rechecked the calculations. Newton's law of gravity, the most successful scientific theory of the age, gives the wrong answer for Uranus. And nobody knows why. The obvious move: sweep the sky with a telescope and find whatever is pulling it. But space is vast and dark. You could search for years without finding anything. You need a smarter plan. What if you could figure out, from pure mathematics, exactly where the invisible object must be? What if you could use gravity like a fingerprint and work backward from the wobble to the cause? In the 1840s, two mathematicians on opposite sides of the English Channel decided to try exactly that. They didn't know each other. They were racing. Without knowing, they were racing. What followed is one of the greatest detective stories in science, a planet found by reasoning alone before a single human eye had glimpsed it. It is also, in its coda, a cautionary tale. Because the same man who found a planet with mathematics would later predict a second planet, using the same method, the same logic, the same confidence that simply did not exist. To understand both the triumph and the failure, we need to go back to a garden in Bath, England, in the spring of 1781, and a musician who accidentally became the most famous astronomer of his century. A discovery was about to happen, not because someone was searching for it, but because someone was paying attention to something small and strange. Which is usually how the big ones work. Pay attention to the loose ends. They are almost never loose. They are usually the edge of something enormous. His name was William Herschel. German-born, trained as a musician, he had developed an obsession, building the finest telescopes in the world, then using them to map the entire sky, star by star. On the night of 13 March 1781, Herschel was systematically cataloging stars when something caught his eye. One object was different. It had a visible disk, not the sharp point of a true star. Herschel noted it, came back to it, and reported it as a probable comet. But comets move in elongated arcs. Other astronomers tracked this object. It was tracing a nearly circular path. Too circular. Too slow. It was a planet. The sixth planet in the solar system. The first ever discovered with a telescope in all of recorded history. A world nearly twice as far from the Sun as Saturn, hiding in plain sight. Now, with a new planet, the first thing you do is compute its orbit. And to calibrate it, you search old records for previous unrecognized sightings. It turned out Uranus had been seen before, and not recognized. The astronomer John Flamsteed had recorded Uranus in 1690, nearly a century earlier, thinking it was just another faint star. Those old, unrecognized sightings were now invaluable data points for building an orbit. But when astronomers combined all those old observations with Herschel's and tried to fit a single clean orbit, they couldn't. The planet refused to sit on a neat ellipse. The discrepancy kept growing. By the 1820s and 1830s, the error was far too large to blame on measurement mistakes. Something was wrong with either the data, or Newton's law, or the solar system itself. Those were the only options. The compelling but speculative answer: an unknown planet farther out, pulling Uranus subtly off course. If it existed, it had never been seen. No telescope had ever caught it. But perhaps it could be calculated. But to find it by calculation, that's genuinely one of the hardest problems in classical mechanics. Working forward for known planets to predict their interactions, that's difficult but doable. Working backward from a wobble to find its hidden cause, that's a different beast entirely. You have to guess the starting position for the unknown planet, compute what wobble it would produce, compare that to what Uranus actually does, adjust your guess, and repeat. Hundreds of iterations, all by hand. In the mid-1840s, two men, on opposite sides of the channel, decided, entirely independently, that they were going to solve it. Let's meet them. John Couch Adams was born in 1809 in Cornwall, son of a tenant farmer. He showed such early mathematical ability that his family found the means to send him to Cambridge University. At Cambridge, he was extraordinary. In 1843, he graduated as senior wrangler, the top mathematics student in the entire university. In Victorian Britain, this was one of the most prestigious intellectual distinctions that existed. That same year, the year he graduated, Adams wrote himself a private commitment. He would investigate the orbit of Uranus. He had just earned his degree, and he was already aiming at one of the greatest unsolved problems in astronomy. For 2 years, Adams worked through the problem methodically. He assumed the hidden planet existed, positioned it in a rough starting orbit, computed the gravitational tug it would produce, and compared that tug to the observed anomalies of Uranus. Adjust. Repeat. By autumn 1845, Adams had arrived at a prediction, a position in the sky where the unknown planet should currently be. Now he needed someone with a telescope to take him seriously. He approached James Challis, the director of the Cambridge Observatory. Challis passed him upward to George Bedell Airy, the Astronomer Royal, Britain's top astronomer, and a man who ran the Greenwich Observatory with clockwork authority. Adams went to Greenwich in October 1845 to deliver his results in person. He made 2 visits. On the 2nd, on the 21st, Airy was home but unavailable, engaged at dinner. Adams left his written prediction with the servant and departed. Airy eventually read it and wrote back. But his reply asked Adams a specific technical question: could the calculation also account for a peculiarity in Uranus's distance from the Sun, not just its direction? Adams, naturally reticent and not gifted at self-promotion, never replied. Airy, who harbored genuine doubts about whether the inverse planet approach would work, didn't order a telescope search. Months passed. Nothing happened. This is one of the great agonizing what-ifs of scientific history. The prediction existed. The planet was findable. All it required was someone to point a telescope at the right piece of sky. Nobody did. Not yet. And while Britain hesitated, across the Channel, a very different personality had been attacking the same problem. Someone who had no intention of hesitating, and every intention of being heard. Urbain Jean-Joseph Verrier was born in 1811 in Normandy. He began as a chemist, then pivoted to celestial mechanics, and he brought a chemist's precision and an almost combative self-assurance to the mathematics of planetary motion. Verrier began his work on Uranus in 1845, a little later than Adams. But where Adams kept his results private, Verrier published as he went, putting his intermediate results into the open scientific literature and building public pressure for action. His method was systematic and exhaustive. He first proved that the anomaly in Uranus's orbit was real, not the result of measurement error. Then, he showed it couldn't be explained by adjusting the masses of the known planets. The residual was irreducible. He then computed what properties the hidden planet must have to produce exactly the observed wobble, an approximate mass, a range of distances from the Sun, and, crucially, a predicted position in the sky for a specific date in 1846. In June 1846, Verrier published a paper giving the predicted sky coordinates of the unknown planet, where to point a telescope. He followed this with a more complete paper on August 31st, giving the full orbital solution. He brought his results to the Paris Observatory. They were interested, but not interested enough to immediately redirect a telescope. Bureaucratic inertia is a force that even mathematical genius has trouble overcoming. So, Verrier did something bold. He wrote a letter, not to France, but to a German astronomer he had never met. Johann Galle, at the Berlin Observatory. His message was direct. Here is where the planet should be. Please point a telescope. Verrier told Galle the planet should appear in the constellation Aquarius, within roughly 1 degree of the given coordinates. That's a specific, searchable patch of sky, about twice the apparent width of the full moon. It was a confident, precise bet. Verrier sent his letter on 18 September 1846. It traveled from Paris to Berlin in 5 days. It arrived at the Berlin Observatory on the morning of 23 September. Galle read it that day. Galle was excited. He wanted to search that very night. His superior, the observatory director Johann Franz Anke, was celebrating his birthday and initially resisted the distraction. He eventually agreed. The telescope was prepared. Galle enlisted a young graduate student who happened to be working at the observatory that night, Heinrich Louis d'Arrest, and d'Arrest immediately made a suggestion that would prove decisive. d'Arrest knew that the Berlin Observatory had recently received a new, unpublished star chart covering exactly that region of Aquarius, the chart Hora XXIX, part of a systematic Berlin sky survey. He suggested they use it. The method was elegant. Galle would call out the position of each object he saw through the telescope. d'Arrest, at the desk, would check each position against the printed chart. Any planet being newly discovered wouldn't be on it. It would be the one object that didn't match. They began. Object after object matched the chart, and then one didn't. Something was in the sky that the chart didn't record. d'Arrest reportedly exclaimed, "That star is not on the map." They tracked the unknown object through the night. By morning, they had confirmed it had moved relative to the background stars. Only a solar system body does that. They had found a new planet. The date was 23 September 1846, and the planet was located within less than 1 degree of where Verrier's mathematics had predicted, approximately 52 arc-minutes from his calculated position. A mathematician in Paris had pointed at a blank patch of sky and said, "There." And there it was. This was Neptune, the eighth planet, the outermost world in the solar system, found not by a lucky sweep of the telescope, but by calculation. The first planet in history discovered by pure mathematical prediction before anyone saw it. The reaction was immediate and enormous. Newspapers across Europe celebrated it as a triumph of human reason. If Newton's gravity was powerful enough to find an unseen planet from 60 years of faint anomalies, it was powerful enough for almost anything. Verrier became a national hero in France. The director of the Paris Observatory called it a monument to French science. Honors came from across Europe. He was 35 years old, and he had just done something nobody had ever done before. And then, from across the channel, came an awkward message. A young British mathematician had solved essentially the same problem a year earlier, and nobody had listened to him. John Couch-Adams had given his prediction to Challis and Airy in 1845. The British astronomical establishment hadn't acted. Now the planet had been found in Berlin, by French calculation. Britain was mortified. A heated public dispute erupted across the channel. France said, Verrier found it. Britain said, Adams was first. The argument became one of the most contentious priority fights in the history of science. Let's lay out the documented facts evenly. Adams completed a prediction in autumn 1845 and gave it to Challis, but it was never published. It existed only as private communication between a student and a few officials. Verrier published his position prediction in June 1846, a public, permanent, citable record available to any astronomer in the world. His complete orbital solution followed on August 31st. That public record is what Galle acted on. There is no serious historical dispute that the chain from Verrier's pen to Galle's telescope to Neptune is unbroken. Verrier sent the letter. Galle and the rest looked, they found it. That is the operational discovery. What is genuine is Adams's independent mathematical achievement. Working from the same data, using the same theory, without any knowledge of Verrier's work, Adams reached essentially the same answer. That's real, and it matters. The modern historical consensus treats both men as mathematical co-predictors, Adams first in time, Verrier first in action. The operational discovery belongs to Verrier and Galle, but Adams's prediction stands independently alongside it. As for Challis, who ran the Cambridge telescope, he eventually began a search in August 1846, weeks before Galle. He actually recorded Neptune twice, on August 8th and again on August 12th. He just didn't know it. Because Challis lacked an up-to-date star chart for that region of sky, he hadn't checked whether any object had moved between sessions. Neptune was hiding in his own data. He had seen it. He had recorded it. He had not recognized it. And here's the broader lesson worth sitting with. Simultaneous independent discovery is not unusual in science. When the tools and data are ready, more than one brilliant mind often reaches the same answer at the same time. Neptune's discovery confirmed something profound. Newton's gravity wasn't merely a description of planetary motion. It was a precision instrument. You could run it backward, from effect to hidden cause, and find worlds you had never seen. Mathematics has a kind of telescope. Flushed with triumph, Verrier turned his attention to another persistent problem in planetary motion, a smaller anomaly, but real, and just as stubborn. And he was quite sure he could solve it the same way he had solved Uranus. Mercury, the closest planet to the Sun, has a peculiar orbit. Like all planets, it traces an ellipse. But Mercury's ellipse doesn't stay fixed. The whole oval slowly rotates over time. The closest point to the Sun, the perihelion, walks forward, orbit after orbit. This is called perihelion precession, and most of it is accounted for. The other planets pull Mercury gravitationally, and their combined tugging causes most of the rotation. That's understood. That's Newton doing what Newton does. But Verrier found that when you add up all the known contributions from all the known planets, the total is slightly too small. There is a leftover, an extra precession of about 43 arcseconds per century that the known planets simply cannot account for. 43 arcseconds per century. An almost incomprehensibly small angle, less than 1/100th of a degree, spread over 100 years. But Verrier's measurements, and later those of Simon Newcomb in 1882, were meticulous. The anomaly was real. Verrier recognized the pattern immediately. He had done this before, an unexplained wobble, a hidden cause. With Uranus, the hidden cause had been Neptune. Mercury's wobble, he reasoned, must point to another hidden planet. He calculated that a small planet orbiting close to the Sun, entirely inside Mercury's orbit, could account for the extra precession. He named this hypothetical planet Vulcan, after the Roman god of fire. Appropriate for something that would be baking in intense solar heat. In 1859, a French amateur astronomer named Edmond Modeste Lescarbot reported seeing a small, dark disk crossing the face of the Sun, a transit, in March of that year. Verrier traveled to investigate him in person. He was convinced by what Lescarbot described. Vulcan had been spotted. Verrier formally announced the existence of Vulcan to the Académie des Sciences in January 1860. Other observers search during solar eclipses when the region near the Sun briefly becomes visible. A few reported possible sightings. Most found nothing. The evidence for Vulcan never coalesced into a coherent orbit. Reported sightings refused to fit a consistent set of numbers. Verrier died in 1877, on 23 September 1877, coincidentally the 31st anniversary of Neptune's discovery, still believing in Vulcan. The planet was never confirmed. Mercury's anomaly remained, open, unexplained. A small, tidy wound in the body of Newtonian physics that just would not close. For decades after Verrier's death, it sat there, waiting. The answer to Mercury's anomaly didn't come from astronomy at all. It came from a completely different direction, from a patent clerk in Bern, Switzerland, who had been thinking for 10 years about the nature of space and time itself. Albert Einstein had been developing a new theory of gravity, not a correction to Newton, a complete reconception. Newton's gravity was a force acting between masses across empty space. Einstein's idea was something far stranger. In Einstein's general theory of relativity, mass doesn't pull on other masses from a distance. Mass bends the fabric of space-time around itself. What we experience as gravity is simply objects following the curved shape of space, the natural path through curved geometry. Near something as massive as the Sun, this space-time curvature is measurable. And in curved space-time, Mercury's orbit precesses slightly more than Newton's flat space formula predicts. The curvature adds a small extra rotation to the ellipse, naturally without any additional planet required. In November 1915, Einstein completed his general theory of relativity and immediately applied it to Mercury's orbit. The result? Approximately 43 arcseconds of extra perihelion precession per century, matching the anomaly precisely, down to the measurement precision available at the time. Einstein had not adjusted a parameter to make the number come out right. He had not tuned anything. The answer fell directly from the theory, untouched. Einstein wrote to his friend Paul Ehrenfest that he had been beside myself with joyous excitement, the words of someone who had just seen their theory touch something real. There was no Vulcan. Mercury's anomaly was not caused by a hidden planet. It was caused by the fact that Newton's gravity, brilliant, accurate, and reliable for 200 years, was an approximation, a superb one, but not the final word. And here's where the two stories, Neptune and Vulcan, become one lesson. Verrier applied exactly the right logical method to Mercury. He saw a real wobble. He reasoned correctly from it. His error was invisible to him, because the error wasn't in his logic. It was in an assumption so foundational that nobody on Earth had questioned it in 2 centuries. Same logical tool. 2 completely different outcomes. Because the tool's validity depends on the theory it runs on, and Verrier couldn't know that Newton's theory had a limit. Let's step back and take in the full arc of the story. In 1846, mathematics pointed at a blank patch of sky and said, "There is a planet there," and there was. That is one of the most extraordinary moments in the history of human thought. Think about what Verrier and Adams actually did. No photographs, no computers, no electronic sky scans, just Newton's equations, 60 years of imperfect handwritten observations, and months of grinding calculation done entirely by hand. At the end of all that paper and ink and thought, someone wrote down a set of coordinates and said, "There. Go look." And the planet was there. This is what mathematics can do at its best. It lets us see things we have no business being able to see. It extends human perception into the darkness, past the range of any telescope, any instrument, any direct observation. And it has happened again and again since 1846. Einstein predicted that massive objects would bend light passing nearby, a consequence of curved spacetime. In 1919, during a solar eclipse, astronomers measured stars slightly displaced from their expected positions. The prediction came before the measurement. Physicists predicted the existence of the Higgs boson in 1964 from quantum field theory, pure mathematics, before any particle accelerator could possibly detect it. The actual particle wasn't confirmed until 2012 at the Large Hadron Collider, nearly 50 years of trust in the math. Gravitational waves, ripples in spacetime produced by colliding black holes, were predicted by general relativity in 1960. Scientists built LIGO and detected them for the first time in 2015, nearly a century of the universe, waiting for us to build sensitive enough ears. Each time, the mathematics reached into the darkness first. The instruments followed. Neptune was not a lucky accident. It was the template, a proof that reason can outrun the eye. But Vulcan reminds us that this power has a condition. Mathematical reasoning is only as good as the theory it runs on. Verrier was doing everything right. His error was invisible to him, because it lay not in his logic, but in physics no one had yet discovered. Science is not a collection of facts carved in stone, it's a living process. Theories are as good as the evidence they explain, and we keep testing them until we find their edges. Newton's model was accurate for 200 years before its edge was found. General relativity has been tested for over 100. Right now, there are anomalies at the edges of what we understand, galaxies rotating faster at their edges than our models predict. The expansion of the universe accelerating in ways that require something we can't yet detect. We call these dark matter and dark energy. Honest names for current ignorance. Maybe those anomalies point to new particles. A new hidden planet, to be found by mathematics before any detector glimpses it. Or maybe they point to something deeper, a flaw in general relativity itself. A new Einstein waiting to rewrite the rules one more time. We don't know which, and that we don't know is not a failure, it's an invitation. It's the universe holding open a door. It's a planet that hasn't been found yet, hiding in the residuals. A planet was once found with a pen. Before a single human eye had ever consciously sought it, mathematics reached into the dark and touched Neptune first. Whatever the next great discovery is, it will probably begin the same way. With a wobble that doesn't quite add up, thanks for spending this time being curious with me. If your mind is full of mathematicians and planets, and the strange distance between what we know and what we're still reaching for, good. That distance is where science lives. Until next time.